Welcome back to this module about pipelining. In this lesson I will explain different possibilities of dealing with branch hazards. First, a quick recap of what we learned in the previous two lessons. We learned that the canonical MIPS pipeline consists of 5 stages: instruction fetch, instruction decode, execute, memory, and write back. We also learned that our assumption is that the register file read takes place in the second half of the ID stage and the register file write in the first half of the write back stage, as indicated by the blue color in this pipeline diagram. This is just an assumption, it doesn't always have to be like that. Moreover, we also learned about pipelining problems called hazards and about possible solutions to these hazards. Structural hazards happen if the hardware doesn't allow the execution of the next instruction in the next clock cycle, and they can be solved by replicating or enhancing the capabilities of functional units. Data hazards occur when there is a dependency with an instruction still in the pipeline, and they can in most cases be solved by forwarding. In case of a load use hazard, however, forwarding cannot solve the day and a pipeline stall may be necessary. Compilers try to avoid such stalls by reordering instructions. Finally, control hazards occur because at the time branches are executed, some instructions have already entered the pipeline. They can be partially solved by executing branches early in the pipeline, and we showed how branch execution can be moved to the second stage of the canonical pipeline, the ID stage. At that time, however, the next sequential instruction has already been fetched. The question then is, what do we do with this instruction? That's the new topic of this lesson. How do we deal with branch hazards? Basically, there are 4 possible ways of dealing with branch hazards. The first is to stall the pipeline until the branch direction is clear. Branches occur frequently, however, so stalling is not the most viable option, especially if performance is our main goal. The second option is to basically predict that the branch will not be taken. This means that we continue fetching and executing the next sequential instruction, but if the prediction turns out wrong, if the branch is actually taken, the wrongly fetched instructions need to be squashed, meaning they should not be allowed to change the so-called state of the processor. The option to predict that the branch will not be taken is illustrated in this figure. In this figure, I assume that branch execution takes place in the execute stage. So when the branch is executed, 2 instructions have already entered the pipeline. If the branch is taken, these 2 instructions need to be squashed, meaning they have to be turned into no operations, very similar to the knob that should occur after the load in a load use hazard. On average, slightly more branches are taken than not taken. Therefore, a third possible branch hazard alternative is to predict that the branch will be taken. In the canonical MIPS pipeline, however, the branch target address is calculated in the second stage, so we cannot decide or predict to jump to this address in the first stage. But there are other processor organizations where the branch target is known well before the branch decision, and on such organization it might make sense to predict that the branch will be taken. The fourth alternative to deal with branch hazards is called delayed branch. This means that the branch actually occurs, meaning if it is taken changes the value of the program counter after a certain number of instructions. Consider this example. We have a branch and the n instructions following the branch in the program text are always executed. In other words, we have a branch delay of n instructions. If the branch is taken, only then the instruction at the branch target address is executed. This is the solution used in MIPS. To be precise, MIPS uses a single branch delay slot, meaning that the instruction after the branch is always executed. This solution was clearly motivated by the design of the first MIPS processor, which was very similar to the canonical MIPS pipeline that we have discussed until now. In it, branches take place in the second stage, and at that time, one instruction has already entered the pipeline. So that instruction is always executed. Later MIPS processors had a very different organization, however. Still, they all implemented this branch delay slot, even though it doesn't really improve their performance. An interesting question is, why? Please think about it. The answer will come later in this lesson. This concludes this lesson. Thanks for watching. In the next lesson, I will describe how the branch delay slot can be filled. Hope to see you back.